Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight we find ourselves beneath a canopy of stars, where each point of light seems to whisper a question older than memory itself. Above us, starlight twinkles across a canvas so vast, so quiet, that it feels like a living thought, stretching outward, always outward. Have you ever tilted your head just slightly and asked, does space end? Is there a border somewhere beyond the stars where the universe simply stops? If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Wherever you are, maybe wrapped in a blanket, listening from a dim room, or drifting on a bus through a sleeping city, we're glad you're here. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin with the sky we all know, a sky that seems familiar and yet unknowable, a sky that has no edge to the eye, no corner to fold into, just a smooth, uninterrupted ocean of darkness sprinkled with stars. From Earth's surface, especially in places far from city lights, the heavens seem to go on forever. And for most of human history, they were thought to do just that. The dome above us, unchanging, infinite, eternal. But as we've built better eyes, first with glass, then with mirrors, then with radio waves and space telescopes, we've come to understand that this sky has depth. It isn't just a ceiling, it's a volume, a living sea of galaxies and gas and gravity. And so the question begins to sharpen. Not just, does space go on forever? But also, where would it stop if it did stop? What would be on the other side? These are ancient questions with no clear answers, but we do know this. The universe has a shape, a rhythm, and a history. And by understanding how space behaves, how it stretches and how it carries light, we might begin to glimpse the contours of this vast unknown. The first step is realizing that space isn't a static container. It isn't a box, and it isn't a stage on which the universe acts. Space is the action. Space moves, breathes, and changes. It stretches, and sometimes it accelerates. This means we can't just imagine the universe like a globe with a boundary or a flat sheet with an edge. Our instincts, formed in rooms, on roads, in forests, aren't equipped for space's geometry, because out here, lines bend, distances stretch, and the very idea of an end becomes slippery. Let's start closer to home. If you step outside tonight and look toward a distant star, the light reaching your eyes might have travelled for hundreds, thousands, or even millions of years. It's like looking into a memory, but not your memory, the universe's. Now look deeper. Look toward a faint smudge of light, like the Andromeda Galaxy. The light from there has taken over 2 million years to get here. That means the Andromeda we see isn't the one that exists now, it's the one that was 2 million years ago. The universe, it turns out, is a memory machine, and the deeper we look, the farther back we go. But here's the twist. Even light has limits. It moves fast, nearly 300,000 kilometers per second, but it's not instant. And that means there's a limit to how far we can see, simply because the universe hasn't existed forever. The cosmos, as far as we understand, began around 13.8 billion years ago. So in theory, the farthest light we could detect would have had just that much time to reach us. And yet, when we map the cosmos, we find that the observable universe has a radius of about 46 billion light years. How is that possible? If the universe is only 13.8 billion years old, how can we see objects farther than 13.8 billion light years away? The answer is as strange as it is beautiful. Space itself has been stretching while the light was in flight. Imagine tossing a message in a bottle across a calm sea. Now imagine that while the bottle is drifting, the sea itself begins to expand. The bottle still reaches you, but it has travelled much farther than you expected, carried not just by its own momentum, but by the very expansion of the sea beneath it. That's what happens with light in our universe. Space is expanding, quietly, gently, but relentlessly. And that means some galaxies we can see now were once much closer to us. Their light began its journey when the universe was younger and smaller. But as that light moved, space expanded around it, stretching the distance it had to travel and stretching the light itself. This is why distant galaxies appear redder than they are. Their light is literally pulled into longer, redder wavelengths by the stretching of space. So, when we ask if space ends, we first have to ask, what is space doing? It turns out it's not sitting still. It's not even staying the same size. It's growing. And that growth means our map of the universe isn't static. It's like watching ripples in a pond, but the pond itself is getting bigger all the time. What we can see is limited. We call it the observable universe, but that doesn't mean it's all there is. Beyond that sphere, those 46 billion light years in every direction, there may be much more. Galaxies that have drifted too far, light that will never reach us, regions of the cosmos so distant, their stories are sealed forever. And this leads us gently to a deeper thought. Maybe space doesn't end. Maybe it simply fades into regions beyond knowing. And if it does end, it might not be a wall. It might be a curve, a fold, a vanishing point where geometry itself changes. Like the horizon at sea, it isn't an edge, just a limit to how far you can see. So we begin here at the velvet border of what we know, and just beyond it, a hush of stars and silence, where the universe continues, or perhaps ends, in a way we're only beginning to imagine. To understand whether space ends, we have to first understand what defines the part of the universe we can see, our observable universe. Imagine standing in the middle of a vast field at night, holding a small lantern. The circle of light around you defines what you can see, not because the field ends there, but because your light simply doesn't reach beyond it. In the cosmos, our light is the ancient glow of the Big Bang, and our limit is set not by lanterns, but by time. The universe is around 13.8 billion years old. That's how long light has been travelling since the beginning, but remember, space itself is expanding. This changes everything. Because the universe has stretched while light has been travelling toward us, the farthest objects we can see today are not 13.8 billion light years away. They're much farther. The current radius of our observable universe is about 46 billion light years in every direction, a sphere of visibility centred on us. This isn't because we're in a special place. Every point in space has its own observable universe. If you could travel to a distant galaxy, it would have a different horizon, a different map, a different sky of what's visible. This observable limit is not a true edge. It's not a cosmic fence. It's more like a fog, a gentle boundary created by time and light. Beyond it we simply can't see, not because there's nothing there, but because the light from those regions hasn't had time to reach us yet, and in some cases perhaps it never will. The speed of light is finite after all, and the expansion of the universe can outpace it. That means some galaxies are receding from us faster than light can travel. Their light, once released, will never arrive. We will never see them, not now, not ever. So even though our view reaches 46 billion light years, the actual size of the universe may be far greater. Possibly infinite, possibly not. But for us, the observable universe is our cosmic horizon, a gentle shell of deep time, a bubble of knowing surrounded by a sea of possibility. When we peer through telescopes like Hubble or the James Webb, we're not just looking across distance, we're looking across time. We're catching light that left its source billions of years ago. The farther we look, the younger the universe becomes, until eventually we reach the earliest light of all. That light comes not from stars or galaxies, but from the moment the cosmos first became transparent. around 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, space was filled with a glowing plasma, opaque and scattered. But once atoms formed, light could finally travel freely. This ancient glow still surrounds us today. We call it the cosmic microwave background. It's the oldest light we can see, a kind of wall in time, a softly glowing sphere far beyond every galaxy that wraps around us like a fossil sky. When we ask if space ends, we often think in terms of a physical border, a wall we might touch. But more often we run into limits of perception, a place where our tools and the rules of physics gently say, no farther. One of these limits is light. But there's another kind of limit too, called a cosmic event horizon. This is different from the observable horizon. The event horizon marks the boundary beyond which events can never influence us, no matter how long we wait. Even if we sit patiently for 1 trillion years, the light from beyond that event horizon will still never arrive, because the space between us and those galaxies is expanding too fast. The distance is growing faster than light can close it. This quiet truth brings with it a strange sadness, a knowledge that some parts of the cosmos are slipping away, not just hidden, but lost to us forever. Yet even in that fading, there is wonder. It tells us that the universe is not a fixed stage. It's a living, growing thing, with a rhythm, a direction, a pulse, and we're inside it, watching it unfold moment by moment. Think of the night sky again. Each point of light is a memory, sent across the deep. The light from distant stars may have begun its journey before Earth had oceans, before our sun had planets, before time meant anything to us. And now, that light touches your eyes. You're part of the story, not just watching the universe, but stitched into it, held in its light, its gravity, its reach. So the question of whether space ends isn't just a mapmaker's riddle. It's a question about what we're part of, and what part of it we can ever touch. There are regions we will never see, moments we will never catch. But still, we look. Our tools reach farther each decade, our senses grow quieter, sharper. We listen not just for light, but for neutrinos, gravitational waves, subtle curves in starlight. We press gently against the boundary of the knowable, and yet, always, there is more. It's possible that space extends forever, that beyond our bubble of knowing, there are endless galaxies, stars, and worlds. That no matter how far you travel, there will always be more space ahead. Or perhaps it loops. Perhaps if you went far enough, you'd end up where you began. Not because there's a wall, but because space is curved, folded back on itself in dimensions we can't fully perceive. We'll return to this idea soon. But for now, let's rest in the notion that the universe we see is only a portion of what might exist. Like standing on a quiet hill, watching fog drift across a valley, you can't see beyond the mist, but you know the land continues. Maybe it rises into mountains, maybe it vanishes into ocean, maybe it just goes on. The night sky's a veil, and the observable universe is what we've managed to glimpse through a crack in that veil. Beyond it, perhaps more stars, perhaps nothing, or perhaps a continuation of something we can barely begin to imagine. As we drift deeper into the question of whether space ends, we find ourselves brushing up against one of the most beautiful ideas in modern cosmology: expansion. The universe is not simply big, it's getting bigger, and it has been for as long as it has existed. This idea began with something small, a few galaxies, a few measurements. In the 1920s, astronomer Edwin Hubble discovered that galaxies are not fixed in place. The farther away they are, the faster they seem to be moving from us. Their light is stretched, shifted into redder wavelengths, a phenomenon we now call redshift. This discovery changed everything. It suggested that space itself is expanding. Galaxies aren't flying through space like sparks from a fire. They're embedded in space and space itself is stretching, carrying them with it. Imagine drawing dots on the surface of a balloon, then gently inflating it. As the balloon grows, the dots move apart, not because they're crawling away from each other, but because the surface between them is expanding. That's a rough two-dimensional metaphor for how our universe behaves. But here's where it gets quietly strange. In this expanding balloon of a universe, there is no central point, no favoured centre. Every galaxy sees every other galaxy moving away. Expansion is uniform. It has no middle, no edge. So if space is expanding, where is it expanding into? The answer is simple, and also deeply unintuitive. It's not expanding into anything. Space itself is growing. New space emerges between galaxies, not in a surrounding void, but from within the universe itself. There is no outside. It's a hard idea to wrap our earthbound minds around. We're used to expansion meaning a thing growing inside a larger thing, a rising loaf of bread inside an oven, a ripple across a pond. But in cosmology, the oven is the bread, the pond is the ripple. Space is all there is, and this expansion leads to a stunning consequence. There is no centre to the universe, no privileged position, no cosmic anchor point. If you were standing on a distant galaxy watching the sky, you'd see the same pattern, everything moving away from you, farther galaxies moving faster. That's not because you're at the centre, but because everyone is. Everywhere is the middle of expansion, and if there's no centre, how can there be an edge? This is the subtle heart of modern cosmology. The universe doesn't expand from a central point outward. It expands everywhere, all at once. Like a stretching fabric without ends. But this raises new questions. Could the universe still be finite, even if it has no edge? Could it be like the surface of a sphere, limited in area but with no boundaries? These aren't just poetic musings. They're active areas of research. To understand them, we have to think not just about expansion, but about geometry, the shape of the universe. According to Einstein's theory of general relativity, the shape of space is determined by its energy content. Matter, radiation, dark energy, all of these influence how space curves. There are three broad possibilities. First, the universe could be positively curved, like the surface of a sphere. In this case, if you travelled far enough in a straight line, you'd eventually end up back where you started, just like circumnavigating the Earth. Second, it could be negatively curved, like a saddle. In this geometry, space continues forever, but with a strange bending that opens outward, causing parallel lines to diverge. Third, it could be flat, with no overall curvature. In this model, space also goes on forever, but in a neutral Euclidean way. Which shape describes our universe? Measurements from the cosmic microwave background, our oldest light, suggest that space is very nearly flat. Not exactly, perhaps, but close enough that any curvature must be slight and subtle on the larger scales. This doesn't tell us whether the universe is infinite. It only tells us that if it's curved, the curve is so gentle we haven't noticed it yet. And so we return to our quiet question. Does space end? Maybe it loops. Maybe it curls into itself in ways our minds can't easily picture. Or maybe it just keeps going, limitless, boundless, without repeat or return. Perhaps we'll never know for sure. But what we do know is this. The universe is growing. It isn't static. It hasn't settled. It hasn't arrived. It continues. And in that continuation we find a strange kind of comfort. Imagine being part of something that has no border, no walls, no outer rim, only expansion, only change. It means we're never quite at the edge. We're always in the middle of something unfolding. The galaxies, like lanterns on a gently rising tide, drift outward in every direction, not racing through space but carried by it, like leaves on a widening stream. The farther out we look, the older the light we see. And the more deeply we're peering into the history of that expansion, One day, perhaps far into the future, even that light will fade. Distant galaxies will slip beyond our event horizon. Their light will no longer reach us. The observable universe will shrink in richness even as space continues to stretch. But that doesn't mean space ends. It just means our view dims, like sitting on a shore as fog rolls in, quiet, inevitable, soft. So here we are, in the middle of this quiet unfolding, a flicker of awareness, wondering about the edge. Maybe there isn't one. Maybe there's only more. If the universe is expanding, and if there's no centre and no edge, then where does that leave us? What are we drifting toward? To answer that, we turn to the galaxies, those distant beacons scattered like fireflies across deep time. We've known for decades now that they are moving away from us, but not just slowly. The farthest ones are retreating at astonishing speeds, some at over 90% the speed of light. And beyond a certain distance, they're receding faster than light itself, not because they're breaking cosmic speed limits, but because the space between us is expanding so swiftly. This gentle stretching of space is a quiet, ongoing process. It isn't like an explosion. There's no debris field, no shrapnel, just a gradual drawing apart like threads pulled slowly through fingers. It's so subtle that we can't feel it in our daily lives. The room around you doesn't stretch. Neither does your city or the solar system or even the Milky Way. Local gravity holds these things tightly bound. But at scales larger than clusters of galaxies, expansion becomes undeniable. Vast regions of space grow more spacious. Voids swell. Galaxies grow lonelier. We see this redshift in the light they emit. As space expands, it stretches the very light moving through it. Blue becomes red, bright becomes faint, ancient becomes distant. These shifts help us map the universe, not just where things are, but when they are. And here lies the wonder. We don't simply see galaxies as they are, we see them as they were. The most distant galaxy ever observed sent its light over 13 billion years ago. Back when the universe was still young, still clearing its throat after the Big Bang. What we glimpse is a memory, fossilized in photons, travelling across all that expanding space just to arrive in our telescopes. Even now, new observations push that limit. The James Webb Space Telescope is peering deeper, chasing redder, fainter light, seeking the very first galaxies, the cosmic dawn when the darkness was just beginning to break. But there's a soft horizon to all of this. Eventually the expansion becomes too much, the light too stretched, the galaxies too faint. They disappear not with a bang but a fade, as if slipping behind a curtain of quiet distance. This is the cosmic event horizon, distinct from the one around a black hole, but eerily similar in concept. It marks the boundary beyond which events can no longer affect us. Not because there's a wall, but because the space between has grown too fast. Light from beyond that veil will never reach us, no matter how long we wait, and the list of unreachable galaxies grows. We live in a golden era of observation. Right now, the universe is young enough, dense enough, and close enough that we can still see the fingerprints of the early cosmos. But that won't last forever. In the far future, perhaps tens or hundreds of billions of years from now, most galaxies will vanish from view. Our night sky will become quieter, dimmer. The stars we know will burn out, and the vast web of galaxies will slip beyond our cosmic reach. This is sometimes called the Big Freeze, a quiet, slow ending, not with destruction, but with isolation. Each galaxy, or group of galaxies, left alone in its own pocket of space, no new starlight, no new warmth, just fading embers in an expanding cold. Does this mean space ends? Not in the way we might expect. It means our experience of space becomes narrower, not because the universe is collapsing, but because it's becoming too vast, too diffuse for its parts to touch. Still, in that lonely future, the universe continues. Space keeps stretching. Perhaps forever. perhaps into something else, perhaps into silence, and that invites a new question. If space is expanding faster and faster, what's causing it? The answer lies in a gentle mystery known as dark energy. We don't know what dark energy is, not exactly, but we know it's real. We see its fingerprints in the way galaxies move, in the way the universe expands, in the subtle geometry of space. It acts like a pressure, not one that pushes things together, like gravity, but one that pulls them apart. A quiet acceleration, spread evenly through the cosmos. It doesn't clump, it doesn't glow, but it's there, in the fabric of space itself, and it may be the key to the universe's ultimate fate. Before its discovery, we thought the expansion might slow over time. Maybe gravity would win out. Maybe the cosmos would stop growing and begin to fall inward, a grand reversal called the Big Crunch. But dark energy changed that story. Now it seems that expansion is not slowing down, it's speeding up. Space is not coasting, it's accelerating. Galaxies are not just drifting, they're fleeing. This means the Big Crunch is unlikely. Instead, we drift toward a long, slow stretching, a future where distances grow infinite, temperatures drop, and time itself stretches thin. Some call this the heat death of the universe, but it's not a dramatic death. It's more like a fade, a sigh, a soft hush after the music ends. And yet, even this isn't the end of space, just the end of interaction, of structure, of light. Space may go on, still expanding, still curving, still existing, even if nothing within it remembers. So again, we ask, does space end? We don't see a wall, we don't see a border, we see motion, we see drift, we see a gentle scattering of light into deep time. That may be all the answer we get. And maybe that's enough. To understand how space might or might not end, we need to go back, farther than galaxies, farther than stars, all the way to the first moments after the Big Bang. Not the bang itself. That's a name we gave to something we still barely comprehend. The Big Bang wasn't an explosion in space, it was space. A moment when energy, time and distance all began to unfold. But shortly after that moment, just a fraction of a second later, something extraordinary may have happened. It's called cosmic inflation. According to this idea, the universe underwent a period of unimaginably rapid expansion. For the briefest sliver of time, less than a trillionth of a second, space didn't just stretch, it ballooned. This inflation expanded tiny quantum fluctuations into the seeds of galaxies and clusters. It smoothed the cosmos. It explains why the universe looks so uniform in every direction, even though light hasn't had time to travel between all its parts. And most relevant to us now, it implies that the entirety of our observable universe may be just a tiny patch of a much, much larger whole. Like a grain of sand on a beach, or a ripple in an endless sea. Inflation is not proven, but it's widely accepted. The patterns we see in the cosmic microwave background, the oldest light, line up beautifully with what inflation predicts. And here's where it gets deeply poetic. If inflation happened once, it may be happening still. Not everywhere, but somewhere, constantly. This leads to the idea of eternal inflation, a concept where different regions of space stop inflating at different times, creating bubble-like universes within a much larger, still inflating multiverse. Each bubble is a universe like ours, each with its own physical constants, its own laws of physics, its own story, and we may never interact with any of them. They are too far, too sealed by inflating space. In this view, space doesn't just continue. It multiplies, it spawns, it becomes a sea of universes, an endless foam of possibilities. So when we ask, does space end? We may be asking the wrong question. It may be better to ask, which space? Because the space we see, the one filled with galaxies and starlight, might be just a sliver of something vastly bigger, a local bloom in a much larger garden. In that larger view, our entire observable universe is like a bubble on the surface of a wave, drifting in a sea of others. Some theorists even propose that the space between these bubbles, the inflating space, is hostile to matter, a place where the normal rules don't apply, a place forever cut off from what we know. And in that picture there are edges, not to space itself but to our pocket of space, edges where the laws change, where the constants of nature no longer hold, but we'll never see them. Those regions, if they exist, are receding faster than light can carry their story to us, and so we're left with the sky we know, the stars we can see, the structure we can trace. Let's return to that for a moment. The large-scale structure of the universe, the way galaxies cluster and stretch, isn't random. When we map the cosmos, we find a vast, interconnected pattern, a structure called the cosmic web. It looks like lace, or frost, or the branching filaments of neurons in a brain. Galaxies and clusters form nodes in this web, connected by long filaments of dark matter and gas. Between them lie enormous voids, immense empty regions, some hundreds of millions of light years across. It's breathtaking, and it's humbling, because even within the part of space we can see, most of it is empty. The stars and galaxies we admire are just specks on an immense scaffold, and that scaffold may extend far beyond what we'll ever observe. Some regions of the web may never come into view, some filaments may never cross the threshold of detectability, but they may still be out there, stretching through an unlit architecture of deep time. There's another quiet question hidden inside all of this. If space might be infinite, what about matter? Does the pattern repeat forever? Are there endless galaxies, stars, and perhaps even lives? Cosmologists don't know. It depends on the total curvature of space, on whether inflation was eternal, on whether there are hidden symmetries we haven't uncovered yet. But the thought itself invites awe. We, who live on a pale world tucked into the spiral arm of an ordinary galaxy, may be part of a structure without end, and yet we only see a piece of it, a thin slice bathed in ancient light. So when we wonder whether space ends, we're also wondering about our place in it. Not just where we are, but how much of the universe we'll ever truly know. For now, our telescopes gather photons, we map, we measure, we listen. But beyond the edge of light, space may continue, not as a room with walls, but as a hush that stretches beyond understanding, a canvas that keeps unfolding even when we stop looking. The universe, in all its grandeur, is not just about what we see, it's about how we understand space itself, and to truly ask whether space ends, we must turn toward its geometry, not just its size, but its shape, its folds, its curvature. Because space isn't flat in the way a tabletop is flat. It's woven into the fabric of time, curved by energy, bent by mass. This is where Einstein's general relativity steps in, a theory that revolutionized our understanding of space not as an empty stage, but as something dynamic, a field that responds to what moves through it. In this theory, massive objects bend space, planets bend it, stars bend it. Even you, resting here tonight, slightly deform the space around you, though by an amount far too small to measure. Now scale that up. The total amount of matter and energy in the universe tells us how space is shaped, and that shape gives us clues about whether space ends or loops. There are three broad possibilities, and each tells a different story. First, the universe might have positive curvature. Like the surface of a sphere, space would loop back on itself. If you travelled in a straight line long enough, you'd eventually return to your starting point, without ever encountering an edge. In this model, the universe is finite in volume but unbounded. Just as Earth's surface is limited in area but has no edge you could fall off, a positively curved universe would have no end, only a graceful return. Second, the universe could be negatively curved. Picture a saddle or the surface of a trumpet. Lines that begin parallel gradually diverge. In this model, space expands outward forever, but without ever forming a closed loop. It's infinite in extent, but with a geometry that stretches outward. Finally, we come to flat geometry. This is the Goldilocks model. Not too curved, not too warped, just neutral, like a perfectly balanced sheet. Measurements from satellites like WMAP and Planck have shown us something remarkable. The universe appears to be very nearly flat. So flat, in fact, that if there's any curvature at all, it's beyond our current ability to detect. But flat doesn't mean small. A flat universe can still be infinite, or it can be finite if it loops in certain dimensions, like the surface of a video game map that wraps around when you walk far enough. We simply don't know. And this unknowing is part of the quiet beauty of cosmology. Even with all our maps, all our sensors, all our carefully tuned instruments, we still face a veil. A soft limit beyond which certainty slips away. And so, when we imagine the end of space, we must imagine not a wall, but a geometry. A structure so vast and subtle that its true form might be forever hidden behind the light we cannot reach. But here's a thought to drift with. If the universe loops, then it might not be endless, but it would still have no edge. You could travel forever without ever hitting a boundary. No fence, no wall, just a return, subtle and slow. In such a cosmos, the journey itself becomes a kind of gentle circle. But if space is infinite, straight and open, then there may always be more beyond every horizon. Galaxies will never see, matter will never detect. And this leads to one of the great paradoxes of cosmology. If space is infinite and filled with matter, why is the night sky dark? This is called Olber's paradox. If there are endless stars in every direction, then shouldn't every point in the sky be filled with starlight? The answer lies in time and in motion. The universe has not existed forever. Light has only had so much time to travel, and distant starlight is red-shifted, stretched and dimmed by the expansion of space. What we see is a dynamic, changing universe, not a static field of endless glow, but a living history unfolding in light and dark. So the darkness of the night sky is not emptiness, it is evidence. Evidence of a beginning, evidence of expansion, evidence that space, even if infinite, still has a story. And we're somewhere in the middle of it. Maybe the middle in time, maybe the middle in space, maybe not the centre of anything, but inside everything, held in the soft fold of geometry, cradled by the quiet drift of space stretching around us. One more thought to carry into the stillness of night. If space curves, it also affects time. Time is not separate from space, it is woven into the same fabric. The more mass or energy nearby, the more slowly time flows. On Earth, your head ages slightly faster than your feet. Clocks tick more slowly near black holes. Time bends with gravity. And on cosmic scales, this bending could mean that not just space, but the story of space has no sharp edge. Perhaps beginnings are illusions. Perhaps endings are horizons we can't quite cross. Or perhaps, in a universe as curved and complex as ours, we are always at the centre, not of the cosmos itself, but of our own path through it. So we sail on, through a geometry still unfolding. Space doesn't end like a road. It turns, flows, stretches, and we, gentle travellers beneath ancient starlight, move with it. As we drift onward through this quiet, expanding cosmos, we begin to sense that the question, does space end, is not just about distance, it's also about light. Not just the starlight we see with our eyes, but a deeper kind of light. Older, colder, and softer. The cosmic microwave background, or CMB, is the oldest light we can detect, a whisper from the infant universe. roughly 380,000 years after the Big Bang, the universe had cooled just enough for electrons and protons to form neutral hydrogen atoms. Before this moment, the universe was opaque, hot plasma scattering photons in every direction. But after, light could finally travel freely. That first free light is still with us. Over the past 13.8 billion years, as space expanded, it stretched those photons, turning them from bright visible light into microwaves. Today they arrive as a nearly uniform glow in every direction, a soft, all-encompassing hum. This glow is not strong enough to light a room, but it is powerful in meaning. It holds the fingerprints of the early universe, tiny fluctuations in temperature and density, which seeded the galaxies and clusters we see today. We've mapped it in exquisite detail. Satellites like COBE, DABQMAP, and Planck have revealed its texture, gentle ripples that hint at the geometry and contents of the cosmos. And these maps help us infer whether the universe is flat, how much dark matter and dark energy exist, and even how old the universe is. The CMB isn't a wall in space, it's a wall in time. It marks the limit of what we can observe directly. Beyond it, the universe was too hot, too dense, too bright for light to travel freely. We can't see past it, not because space ends, but because light couldn't yet begin its journey. In that sense, it's the closest we come to a cosmic veil, a quiet border not of material, but of memory. But even there, space continues. The universe existed before the CMB, and it exists beyond the CMB. We just can't see it in light. That's where other messengers come in. Particles like neutrinos, ghostly and elusive, may carry information from even earlier epochs. Gravitational waves, ripples in space-time itself, may one day reveal stories from those first moments, perhaps even from inflation, or from the merging of primordial black holes. These signals are delicate, rare, but they offer us a kind of cosmic hearing when our sight fails, and they remind us the universe doesn't end at the edges of our vision. There are quiet voices still arriving, whispers of earlier times. The CMB also reminds us of something deeper. Our position in the cosmos is not unique. Wherever you are in space, the background appears the same glow, the same temperature, the same cosmic past. This cosmic principle, that the universe is homogeneous and isotropic on large scales, tells us that there's no center, no edge, no special location. It's as if the universe, like a vast and endless sky, has no front or back, no up or down. And if space has no privileged center, then the idea of an end becomes more elusive, not a place we can reach, not a border we can cross, but maybe a horizon that slips farther away the more we chase it. Still, the CMB surrounds us, whispering the same quiet truth. You are inside the unfolding. This glow, so faint it can only be detected by precise instruments, is the afterglow of the beginning, and it's everywhere. Even now, photons from the CMB pass through you, through your room, through the earth, a soft rain of ancient light, always falling. It's not warm, it's not bright, but it's persistent, and it carries with it the shape of the universe. When scientists study its subtle variations, one part of the sky just slightly warmer than another, they uncover clues about the structure of space, tiny temperature changes, fractions of a degree, but they reveal the fingerprints of deep time, of cosmic inflation, of density waves, of gravitational lenses, and of the earlier structures, clouds of gas that would one day become galaxies. In this way, the CMB is more than just a background. It is a foundation, a quiet cosmic light still echoing through the fabric of space. And it reminds us that even if we can't see the end of space, we can glimpse its beginning, or at least assure the moment when light first broke free. And perhaps that's the more meaningful boundary, not a border at the edge of distance, but a threshold in time, a line where memory begins And if we think of space as something that remembers, then we are part of that memory too, stitched into the glow, reflected in its temperature, held in its expanding silence. We may not know how space ends, but we can feel in the CMB that space had a moment when it first spoke, and it has never stopped whispering since. As we continue drifting across the fabric of space, carried gently by time and thought, we begin to notice how even light doesn't always travel in straight lines. Something subtle happens as starlight moves through space. It bends, it curves. It's guided not by a path of its own choosing, but by the mass around it. This is known as gravitational lensing, a quiet, invisible sculptor of cosmic vision. Imagine looking at a distant galaxy through the lens of a glass marble. The light warps, distorts, sometimes even forms arcs or rings, not because of the marble, but because of a massive object like a galaxy cluster bending space itself. The cluster doesn't just pull on the galaxy, it pulls on the space between us and the galaxy, and since light always travels through space, its path curves with that distortion. What we see is a kind of cosmic mirage. Galaxies that appear stretched, doubled, or even smeared into graceful arcs of light. In some rare cases, the alignment is so precise that the background galaxy appears as a perfect circle of light, a phenomenon called an Einstein ring. But these effects aren't just beautiful, they're powerful tools. By studying how light bends, astronomers can map things that are otherwise invisible, like dark matter, the mysterious substance that doesn't emit light but has mass, and therefore gravity. Gravitational lensing acts like a fingerprint, revealing where dark matter clumps and gathers, even when we cannot see it directly. In this way, the shape of space becomes a kind of map, etched not in ink, but in how starlight is redirected. It's a quiet reminder that what we see is never the whole picture. Sometimes, even in the vast stillness of space, our view is distorted, gently, by forces too large to touch and too invisible to hold. Lensing also tells us something about depth. Space is not a flat canvas, it's layered, curved, alive. A galaxy billions of light years away can shine through the gravitational shadow of another galaxy. Closer to us in time, their light overlaps, their histories intersect in our telescopes. And in that overlap we read the contours of the universe. Like braille under our fingers, there's a deep stillness in this kind of seeing, because we're not just looking at objects, we're looking at space itself, and how it behaves. And space, it turns out, responds to mass, to motion, to energy. That's why light bends, why time slows near heavy things, why black holes curve space-time into a trap no light can escape. And perhaps, why space might never truly end. Because if space can be shaped, by matter, by gravity, by light, then maybe it isn't a thing with a boundary. Maybe it's a relationship, a field, a condition, something that doesn't end, but simply fades where it's no longer meaningful, where there's no more motion, no more difference. And gravitational lensing brings us a little closer to that thought. It shows us that the universe is layered, that time itself has structure, that when we look far enough we're also looking through gravity, through history, through hidden scaffolds of dark matter and unseen forces. And in all this quiet bending we see the universe's softness, not weakness, but subtlety. It doesn't scream, it whispers, curves light gently, alters time delicately, like a tide that rises without sound. And here's something tender to remember. Some of the galaxies we see through gravitational lensing no longer exist. Their light left them billions of years ago, long before Earth had formed. That light has travelled across expanding space, bent around massive galaxies, curved through warping space-time, just to arrive in our instruments, like a message in a bottle carried by currents too vast to name. So when we gaze at those arcs and echoes, we're not seeing objects, we're seeing memories, and we're seeing the shape of the void they pass through, because space has no colour, no sound, no smell, but it has a shape, and lensing is one way we trace it. Another quiet gift of gravitational lensing is that it sometimes lets us glimpse what we otherwise couldn't. It magnifies, amplifies, reveals. We've seen galaxies farther away than we ever expected, not because our telescopes grew stronger, but because the universe itself lent a hand. It bent the light. It brought the message closer. Space, in that way, is not just something we cross. It's something that helps us see. And perhaps, if space does not end, then it continues, not in distance alone, but in layers, in structure, in complexity. Lensing reminds us that space can carry memory, that it can hold impressions of events long past, that the weight of a galaxy can leave a fingerprint in the light of another, and that through all this bending and warping, the universe remains whisper quiet. It never forces itself to be known. It simply lets us trace its shape, one gentle curve at a time. As we move gently through these ideas, lensing, expansion, background light, there's something else, something even smaller, even quieter, that carries the potential to explain why space looks and behaves the way it does. It begins not with stars or galaxies, but with the tiniest ripples in existence, quantum fluctuations. Long before stars formed, before galaxies took shape, and even before atoms came together, the universe was filled with energy, raw, dense, and wildly active. At this smallest scale, the quantum realm, nothing is ever truly still. Even what we think of as empty space teems with fluctuations. Little pulses of energy that appear and vanish unpredictably, like soft static in the silence of the vacuum. And during the brief, explosive burst of cosmic inflation, these tiny fluctuations were stretched across space. They were magnified from subatomic scales into galactic scaffolding. They became the blueprint for everything. From this, we believe the entire cosmic web was born. The first ripples in the universe were not from stars colliding or galaxies merging, but from the jittery uncertainty of quantum fields. In this view, the very structure of space was seeded by randomness, by possibility. This randomness, magnified by inflation, meant that some regions of space had slightly more matter than others. These denser regions would over time attract more matter, becoming the galaxies, clusters and filaments we see today. So in a sense, the entire visible universe may have emerged from soft, unpredictable whispers, not design, not certainty, but potential. And if quantum fields can ripple once, they might ripple forever. Some cosmologists believe that these fluctuations don't just seed structure, they may seed entire new universes. In certain models, as inflation ends in one region, it continues elsewhere. A single fluctuation can bubble into a new pocket of space, a new universe, forever branching, forever expanding. This idea gives rise to the concept of a multiverse, where different regions of space give rise to different laws of physics, different outcomes, perhaps even different versions of time. Each universe in this vast foam of possibility begins as a single quantum ripple, and each might be infinite in its own right. If this picture is true, then our universe is not the universe. It's one of countless blooms, each born from a vacuum that never truly rests. It's a humbling idea, that the fabric of our own space, so enormous, so complex, may have been born from something as ephemeral as a tremble in a quantum field. It also reminds us that space is not empty. Even the vacuum has energy. Even nothing is something. And this quantum vacuum energy may be what fuels dark energy, the mysterious driver of the universe's accelerating expansion. It could be that the same restlessness that gave birth to galaxies is also pushing them apart. That expansion and creation are two sides of the same whisper. So when we ask whether space ends, we're also asking, does possibility end? Because if quantum fields ripple eternally, then space may too. Not necessarily in the way we experience it with galaxies and stars, but in the sheer potential for more fluctuations, more expansion, more structure emerging from silence. And while these ideas may seem distant, they're connected to us in subtle ways. The very atoms in your body were born from stars. But the placement of those stars, the architecture of galaxies, the very reason there is structure instead of smoothness, that all traces back to those early quantum whispers. You are quite literally built from the imbalances of deep time. Had the fluctuations been slightly different, had the early universe been smoother, there might have been no galaxies, no stars, no planets, just quiet, just hydrogen. But because of those little ripples, space has texture, and texture makes memory possible. It makes clumping possible, matter coming together to form things, worlds, eyes to see those worlds, ears to hear the soft hum of starlight, and minds that ask questions like this. Does space end? Or does it bloom again and again from the smallest, faintest stirrings in the void? We may never know for sure. But we can say this, even in the deepest emptiness we can imagine, there is still the capacity for birth, for shape, for the slow unfolding of structure from silence. And that is the story of space too. Not just vastness, not just size, but the quiet act of becoming. So far we've wandered through expanding galaxies, subtle geometry, ancient light, and the tremble of quantum fields. And yet, something quietly important remains. The limits of what we can know. Because if space does end, or doesn't, how would we ever tell? We live inside a universe that may be infinite, or it may be finite yet unbounded. Or perhaps it's just one region in a much larger multiverse. But no matter which is true, our observations are confined to a small, shimmering bubble, the observable universe. This bubble, stretching 46 billion light-years in every direction, defines the edge of our cosmic sight, not because it marks the end of space, but because it's as far as light has travelled since the beginning of time. Beyond that, we can only imagine. Maybe the same patterns continue, galaxies upon galaxies, a never-ending lace of stars. Maybe space loops back on itself, curving into a four-dimensional shape that we can't visualize, where straight lines eventually return home. Or maybe, just maybe, space fades out. Not into a wall, not into blackness, but into something unmeasurable. Into regions without structure, without matter, without motion. A kind of mathematical silence. This is where cosmology becomes not just a science, but a meditation. There are truths we can't reach, not because we haven't built a big enough telescope, but because of the horizons space itself creates. Some of these are practical, like the cosmic event horizon, beyond which light will never reach us. Others are conceptual, like the possibility that we're limited not by distance, but by the very rules of physics that shape what can be observed. And yet the universe still gives us gifts. Every photon that reaches our instruments, every faint galaxy revealed by a long exposure, is a message from that soft unknown. Like a firefly blinking at the edge of a field. It may not tell us what lies beyond the trees, but it reminds us that something is there. There's a special kind of light that plays with these boundaries. Not just photons, but gravitational waves. Ripples in space-time itself. First predicted by Einstein, these waves are caused by massive objects accelerating, like black holes spiraling together, or neutron stars colliding. And in 2015, humanity caught one. A faint stretching ripple in the fabric of space detected by LIGO. It was as if the universe itself had briefly breathed, and we noticed. These waves offer a new way to see. A new sense attuned not to light, but to motion through the cosmos. And unlike light, gravitational waves are less easily blocked. They travel through dust, through stars, through the fabric of the cosmos with elegant indifference. They may one day help us probe regions of space and time hidden from ordinary observation. Just as a whisper in a quiet room reveals presence, gravitational waves remind us that space is not still. It shudders, it flexes, it carries information through those subtle shifts, and each wave we detect adds another thread to our tapestry of understanding. Another sign that even the farthest reaches, though unseen, are not silent. So perhaps, in the end, it isn't the question of whether space ends that holds the most meaning. It's the way the universe responds to our listening, with echoes, with curves, with signals faint but clear. In every photon a story, in every gravitational wave a motion, and in every unanswered question an invitation. An invitation to wonder, to explore, to rest our minds on something too vast to hold and too soft to resist. And perhaps that is the true shape of space, not flat or curved or infinite, but open to interpretation, open to mystery, open to the kind of curiosity that doesn't demand an answer, but finds comfort in the drift. We're not outside the universe trying to measure it from afar. We're inside it, of it, moving with it, a wave upon its surface, a flicker within its thought. And that closeness, that belonging, may be all we need. So when you next look up at the sky and feel the question return, does space end? You might smile at the stillness above you. Because even if there's no final wall, no cosmic edge, there is always something more. More stars to see, more light to chase, more silence to listen to. And maybe, just maybe, that's the point. To think about the possible end of space is to also reflect on how we travel through it. Not with ships, perhaps, but with thoughts, with instruments, with the patient light of stars. And in this quiet movement through space and time, our own solar system becomes a kind of resting point, a familiar shoreline from which we peer into the deeper ocean of the cosmos. Let's settle there for a moment, among the planets, the quiet moons, the dark stretches between worlds. Beyond Neptune's orbit lies a region called the Kuiper Belt, a cold, distant collection of icy bodies, dwarf planets, and comets. Pluto lives here, along with Eris, Haumea, Makemake, and countless others too small to name. But the Kuiper Belt is not the true edge. Farther still lies a more mysterious structure, the Oort cloud, a vast theoretical shell of icy objects surrounding the solar system, stretching perhaps halfway to the nearest stars. We haven't directly observed it, but we infer its existence from the behaviour of long-period comets, wanderers that arrive from far beyond the planets, from orbits tilted and stretched in ways no nearby object could explain. If it exists, the Oort cloud may represent our local edge, our own solar horizon. But even here, the concept of an edge is blurred. The Oort cloud doesn't end sharply, it just thins. Objects become more distant, gravity weakens, the solar wind slows and mingles with the wind from other stars. Eventually the influence of our sun fades into interstellar space, but space itself, it continues. Even beyond the heliopause, where the sun's particles give way to the wider galaxy, there is no wall, no edge to push against, just a transition, a soft gradient from one influence to another. It's the same across scales. From solar systems to galaxies, from galaxy clusters to cosmic filaments, the structures we build in our minds don't end so much as they dissolve. They blend into something larger, more diffuse, and that dissolution is deeply comforting, because it means nothing is truly isolated. Everything is part of something greater. Everything continues. Even a single comet in the Oort cloud, frozen, dark, forgotten, still belongs. It still orbits. It still feels the faint pull of the sun. And who knows? Perhaps one day it will drift inward, past the outer planets, glow briefly with sunlight and vanish again. A quiet visitor from the edge. This sense of quiet continuity is echoed in the way galaxies behave. take our own Milky Way. It doesn't sit alone in space. It belongs to a local group, a small cluster of galaxies including Andromeda and dozens of smaller companions. Together we drift through space bound by shared gravity, and beyond that, the Virgo supercluster. One of many vast lattice-like formations woven into the cosmic web. But even these superclusters are not edges, they're the most luminous threads in a wider fabric. Between them stretch immense voids, regions where galaxies are rare and matter is diffuse. These voids are not empty, just quieter, softer, less structured. But they too are part of the universe, part of space, part of what continues. In this way, the end of something often looks more like a fading, from dense to diffuse, from luminous to dark, from active to still. So perhaps we should stop thinking of edges as walls and start thinking of them as thresholds, places where influence wanes, where structure quiets, where one story fades and another begins. In deep space, this principle holds true in surprising ways. For instance, take Lagrange points, special positions in space where gravity balances perfectly. Here, objects can remain relatively still, caught in the gentle equilibrium between larger bodies. There are 5 such points between the Earth and the Sun, and others between any 2 orbiting objects. They're not boundaries in the traditional sense, but they represent places of pause, of balance, of stillness. Even here, space doesn't end, but its behavior changes, it slows, it holds, it rests. This is perhaps the deepest truth of space. It is not about borders or edges, but about patterns of motion, about where influence holds and where it lets go. The further we travel, whether by spacecraft or by mind, the more we encounter this gentle truth. Even Voyager 1, the most distant human-made object, now travelling through interstellar space, has not left space. It has only moved from one kind of environment to another. It crossed a threshold, not a wall. It still moves, still sends signals, still belongs. In a universe where everything flows, where gravity curves and light bends and structure fades, we begin to understand. Perhaps space was never meant to end. Perhaps it simply changes, and we with it. Imagine just for a moment that space did have an edge. What would it look like? Would it be a wall, a sharp drop-off, a shimmering boundary beyond which nothing exists? Or would it be something stranger? Cosmologists have long wondered how to even define an edge of space. After all, space isn't made of stuff in the ordinary sense. It's not a fabric you can touch, or a surface you can lean against. It's a framework, an arena in which matter and energy interact. So what does it mean to say that it ends? In Euclidean terms, when we imagine space, we tend to picture something like a room, a volume with dimensions, maybe infinite, maybe not, but still a kind of container. That's how our minds work. We live in rooms, we walk along roads, we measure distances between objects. But when you move far beyond human scales, into the deepest cosmological realms, those metaphors start to fail. Take the idea of a finite but unbounded universe. It sounds contradictory, but it's not. Think of the surface of a sphere. It's finite in area. You could walk around it and eventually end up where you started. But there's no edge, no cliff, no wall, just gentle curvature. In the same way, space could be finite in volume, but loop back on itself in higher dimensions we can't directly perceive. If this were the case, then light travelling in a straight line long enough might eventually return from behind, like walking in one direction on Earth and arriving back at your starting point. Of course, we haven't observed this. The universe appears flat, and we haven't seen the telltale signs, repeating patterns in the cosmic microwave background, for example, that would indicate such looping. But the possibility remains, and it challenges our instincts, because it means edges might not be physical boundaries, but limits of perspective, not endings, but places where direction becomes circular. Now let's suppose, just for a breath, that space does end. Really end. What lies beyond it? The question becomes slippery, because space and time are part of the same fabric. They were born together, and they may only exist inside the universe. So asking what's outside the universe might be like asking what's north of the North Pole, a place beyond place, a direction that doesn't exist. Still, we can imagine. Beyond the edge there might be nothing, not a vacuum, not empty space, but true nothingness, no distance, no time, no direction, a state beyond experience, beyond physics, beyond meaning. Or perhaps there is something, another bubble, another universe, another set of rules, a region where time flows differently, where matter is arranged along unfamiliar lines, where gravity behaves in ways we can't yet grasp. In this vision, our universe is like a snow globe floating in a vast sea of possibility, a foam of universes, a multiverse. In some versions of this idea, rooted in theories like eternal inflation, new universes are constantly forming, sprouting like buds from a quantum field, each one with its own space and time, its own expansion, its own internal physics. In that case, our cosmic edge wouldn't be the end of everything. It would just be the edge of our particular region of space-time. Beyond it lies other space, not ours, not reachable, but still something. There's even the possibility that our universe is a kind of brain, a surface floating in a higher dimensional space. In string theory, our universe might be just one of many such brains, moving through a bulk space we can't perceive. These are not just wild guesses. They're attempts to explain patterns we observe, laws we uncover, behaviours we struggle to reconcile. And while none of them are proven, they hint at one core idea. The universe may be more layered than we ever imagined. So if space ends, if there truly is a boundary, it may not be a flat edge. It may be a transition into another kind of being, another set of dimensions, another way of organising reality. But even if we never cross it, even if we never touch it or observe it, it shapes how we think. It reminds us that the known is always nested within the unknown, and that what seems infinite may be part of something larger still, or smaller, or stranger. So perhaps the question isn't, does space end? But how deep is space? Not in terms of kilometres or light years, but in complexity, in richness, in possibility. And in that depth, maybe there is no edge, only layers, only thresholds, only a gentle unfolding from what we understand to what we don't. And maybe that's how the universe prefers it. No walls, no fences, just an open invitation to explore, to wonder, to drift. Even as we drift through theories of edges, boundaries and multiverses, one quiet force continues to shape the fate of space: dark energy. It is, in many ways, the most elusive part of our cosmos. It does not shine. It does not clump into stars or galaxies. It cannot be touched, held, or seen. But its presence is undeniable. We see it not directly, but through its influence, through the way the universe behaves on the larger scales. Dark energy is the name we've given to the force behind the accelerating expansion of space. Yes, expansion isn't slowing down, it's speeding up. This discovery came as a surprise in the late 1990s, when two teams of astronomers studying distant supernovae noticed something strange. The light from these stellar explosions was fainter than expected, not because they were intrinsically dim, but because they were farther away than they should have been if the universe's expansion were constant or slowing. Something was pushing galaxies apart faster over time. That something became known as dark energy, and it now makes up about 70% of the energy content of the universe. But we don't know what it is. It might be a property of space itself, a cosmological constant as Einstein once proposed. Or it might be something dynamic, an evolving field that changes over time. Some even speculate that it's a temporary phenomenon, that dark energy may someday fade, reverse, or behave in unexpected ways. But for now, its effect is clear. Space is stretching faster and faster. Galaxies that are already distant will eventually slip away, receding beyond the point where their light can ever reach us. The universe, once a connected web of galaxies, will become a collection of isolated islands, each one surrounded by silence, and the farther into the future we go, the quieter space becomes. This is one version of the universe's fate, the big freeze or the heat death. In this scenario, stars gradually burn out, black holes evaporate, matter decays, and the fabric of space continues to stretch toward a cold, dark stillness. It's not a violent end, it's not dramatic, it's gentle, quiet, long, a slow hush falling over the cosmos. But even in that fading, space continues. It may become too diffuse to form new stars, too empty to sustain life. But it will not stop. It will not end. It will simply change. That's the core rhythm of the universe, transformation. And dark energy is one of its most mysterious instruments. Some theories propose that dark energy is tied to the vacuum energy of quantum fields, the same subtle buzz that gave rise to the universe in the first place. Others suggest it could signal new physics entirely, clues that our understanding of gravity, time, or space itself is incomplete. There's even a more speculative idea, the Big Rip. In this version, dark energy's influence increases over time, so much so that it eventually tears galaxies apart, then solar systems, then atoms. Not all physicists support this model, and current observations suggest the universe may be safe from such a dramatic unravelling. But it's a reminder that space is not a static backdrop, it's an evolving stage, a living field, and the fate of that field, how it changes, how it stretches, shapes everything that happens within it. It also shapes the meaning of an edge, because if dark energy continues to push space apart faster and faster, there will come a time when every observer becomes cosmically alone. In tens of billions of years, the only galaxies visible from Earth or any other galaxy will be those gravitationally bound to it. Everything else will fade beyond detection. In that future, it will be as if the rest of the universe ended. Not because it was destroyed, but because it simply drifted too far, too fast, too quietly. Imagine looking up at the night sky in that distant future and seeing only one galaxy, your own. No clues that a vast cosmos ever surrounded you. No signs of a universe that once teemed with light. This scenario reminds us of something important. The boundaries of space are not just physical. They are experiential. They depend on where you are, when you are, and how you observe. Right now, we are in a privileged moment, a brief window in cosmic time when the sky still reveals its richness. We see clusters of galaxies. We map the cosmic web. We measure the whisper of the cosmic microwave background, but these windows do not stay open forever. The expansion of space driven by dark energy gradually closes them, softly, inevitably. So when we ask whether space ends, we might also ask, how much space will remain visible to us? How much will we be able to experience? And how does that change our understanding of where we are? In the presence of dark energy, the map of the cosmos is not a fixed thing. It's a breathing, shifting story. A story that changes with time. A story in which we are part of the plot, however quietly. As we drift further into the fabric of space, we find ourselves approaching a future that feels both silent and immense. A future shaped not by explosion, but by slow fading. This idea, often called the Big Freeze, is perhaps the quietest of all cosmic endings. There's no dramatic crash, no sudden stop, just a gradual unfolding of silence. It begins, as it already has, with expansion. The galaxies drift apart, carried by the invisible stretch of space. Over time, their light thins, their gravitational ties weaken, and eventually many will slip beyond our cosmic event horizon. One by one, these distant galaxies will disappear from view. Not because they've vanished, but because their light can no longer reach us. The space between has grown too vast, expanding faster than even photons can bridge. And so, slowly, the universe becomes dimmer. Stars will still burn, of course, at least for a while, but even that has a limit. Our sun has about 5 billion years left before it exhausts its hydrogen. Larger stars live shorter lives, burning through their fuel more rapidly and ending in supernovae or collapse. Smaller stars, the quiet red dwarfs, will linger far longer, some for trillions of years. But no star can burn forever. Eventually every light will go out. What remains? White dwarfs, slowly cooling. Neutron stars, dense and quiet. Black holes waiting in the dark. As time stretches on, even these will change. White dwarfs will fade into black dwarfs. Cold, invisible embers of once luminous stars. Neutron stars may collide, sending out brief flares of energy, and then nothing. Black holes, once the devourers of matter, will begin to evaporate through Hawking radiation, releasing faint particles until they too are gone. The timescales for these events are beyond comprehension, quadrillions of years, but the process is not rushed. The universe is in no hurry. It simply cools, it stretches, it rests. In the final chapters of the Big Freeze, even atoms may decay. Protons might break apart, leaving only radiation and elementary particles drifting in the dark. The universe, now vast and empty, will continue to expand, cold, smooth, structureless. But again, we must ask, is this truly an end? Or is it just another phase? After all, the cosmos has already transformed many times. It began as a hot, dense point, then a soup of particles, then atoms, then stars, then galaxies. Each phase gave rise to the next, so why should this future stillness be final? Some theorists suggest it might not be. Perhaps, in the far future, quantum fluctuations will once again stir the void, creating a new bubble of space and time, a new universe emerging from the vacuum. Or perhaps, as space stretches and thins, it becomes unstable in other ways, causing a fundamental shift in the laws of physics, a new phase transition that rewrites everything. There are even ideas that time itself might begin to behave differently, that entropy, the great driver of disorder, may reset or reverse. But these are speculations. Beautiful, yes, but still uncertain. What we do know is that the arrow of time as we experience it seems to point toward increasing entropy, toward more disorder, toward silence. Yet even in this imagined stillness there is something oddly comforting, because the story of the universe is not one of sudden endings, but of transformation. Everything that fades was once bright. Everything still is part of something larger, and even in the coldest, emptiest reaches of space, the memory of light remains. The atoms in your body were forged in stars. The oxygen you breathe once flowed through solar winds. The calcium in your bones once sparked in the collapse of a dying giant. You are in every sense a product of motion, of heat, of expansion. So as the universe fades, you might wonder, what remains? Perhaps not the stars, but perhaps the structure that shaped them. Perhaps not the galaxies, but the imprint of their dance, and perhaps not us, but the quiet trace we leave in space's unfolding story. There is something humbling in this, something deeply still, not a death, but a sigh, a hush, the same hush you feel at the edge of a forest at night, where the light is gone, but the presence remains, where the sky above whispers of stars you can no longer see, and yet you know they were there, and that is enough. From the cold reaches of the far future, let us drift back, not in time, but in concept, to a different kind of idea, one where the universe never truly ends because it is always beginning. This is the heart of the theory known as eternal inflation, a picture of the cosmos not as a single event, but as an ongoing bloom of realities, each one budding off from a larger, ever-expanding field. To understand this, let's gently revisit inflation, the process we touched on earlier. Shortly after the Big Bang, the universe likely underwent a burst of exponential expansion, growing unimaginably fast in a fraction of a second. This period of rapid inflation smoothed out space and seeded the conditions for everything that followed. But according to some models, that inflation never ended everywhere. Instead, it stopped in some regions, allowing universes like ours to form while continuing in others. Those regions where inflation slows give rise to bubbles of space, each one with its own laws of physics, its own constants, and its own unfolding timeline. And if inflation is eternal, then this process never stops. New bubble universes continue to emerge within the broader inflationary sea, each one isolated, each one vast, each one infinite perhaps, in its own right. We live in one such bubble, our space, our time, our stars, our silence. But beyond our bubble, other spaces, other times, other silences. This is not science fiction. It's one of the serious possibilities emerging from attempts to reconcile inflation with quantum physics and general relativity. The mathematics doesn't rule it out. In fact, it suggests that such a multiverse might be the natural result of how inflation behaves at quantum scales. So what does this mean for the idea of an end to space? In a universe governed by eternal inflation, space never ends, because there is no single space. There is only our space, and beyond it, unreachable and forever separate, are countless others. Perhaps they are sterile and empty. Perhaps they flourish with galaxies like ours. Perhaps they are strange beyond imagination, governed by unfamiliar rules, different particles, different dimensions, even different forms of time. And while we can never interact with these other universes, no signal can cross the inflationary barrier, they still offer something profound. They expand our sense of reality. They remind us that our visible universe, with its 100 billion galaxies, may be a mere ripple in a much vaster ocean. And that ocean is still swelling, still blooming, still birthing new universes from the deep vacuum. In this model, space doesn't stop, it multiplies. It's not a singular structure, but a process. Not a thing, but a gesture. A continual unfolding of possibility. This idea connects with certain versions of string theory too. In those models, there are many ways for the extra dimensions of space to compactify, each configuration giving rise to a different universe with its own properties. Add to that quantum uncertainty, and you have a recipe not just for one cosmos, but for a whole landscape of them. A cosmic field, blooming with realities, and yet we may never leave our own. Our cosmic horizon still defines what we can see. The multiverse remains a mathematical whisper, a conceptual boundary, not a physical one. But the idea carries weight, even here in this still moment, because it reminds us that our universe is not inevitable, its laws are not guaranteed, and its boundaries may not be the final ones. Perhaps beyond every horizon there are more horizons, not stacked in space but layered in possibility, not floating in void but emerging from it. This reshapes how we think about scale. If space is part of a multiverse, then asking whether it ends becomes a different kind of question. Not where does it stop, but how deeply does it branch? Not how far does it go, but how endlessly does it begin? And in that reframing, something soft arises, a sense of being part of a grand, ongoing blooming, a petal on a flower in a garden we'll never fully walk through. And yet, that petal is enough. It holds stars. It holds light. It holds you. So tonight, as we listen to the silence between galaxies, let us also listen to the silence beyond galaxies, the hush between universes, the pause between possibilities, There may be no map to that space, but it might be the most infinite of all. As we glide through this vast and layered cosmos, we've seen how space can stretch, curve, ripple, and perhaps even multiply. But space is only half the story. The other half is time, and the two are not separate. They are threads in the same fabric, woven together into something we call space-time. Everywhere there is space, there is time, and where time flows, space is shaped. They are not passengers on the same road, they are the road. This idea lies at the heart of Einstein's general theory of relativity. Mass bends space, and it bends time too. A planet doesn't just sit in space like a marble on a table, it warps the fabric of space-time around it, like a heavy ball on a trampoline, and anything moving nearby follows the curve it creates. But time flows differently depending on that curve. This means that space doesn't just change where we are, it changes when we are. And this becomes especially important when we ask whether space ends. Because the end of space, if it exists, would likely also involve a change in time, maybe even an end to time itself. But what does that mean? In everyday life, we treat time like a river, always moving forward, always ticking at the same pace. But on cosmic scales, that river can bend, slow, even split. Time moves more slowly in strong gravitational fields. On the surface of a neutron star, for example, a single second would feel much longer to an outside observer. Near a black hole, time slows dramatically, and at the very edge of a black hole, the event horizon, time, from the outside perspective, nearly stops. This idea stretches the imagination, because if space has curvature and time is part of space, then time has curvature too. Time is not a simple arrow, it is a dimension, and perhaps, like space, it could also have an edge. Some physicists have wondered whether the beginning of time at the Big Bang might be mirrored by an end in the far future, a place, or more accurately, a moment, beyond which time no longer flows. Not because something explodes or collapses, but because the structure of space-time no longer supports the flow we call time. It's a soft ending, a slowing, a pause, a fading rhythm. If space expands forever, thinning and cooling, then time may do something similar, not end abruptly, but flatten. Like music slowing into a final note stretched so long, it becomes silence. And here's a quiet idea to hold in your thoughts. If space is curved enough, it could fold back on itself in time just as it might in distance. In such a universe, the future and the past could be connected. Time might loop like a ribbon, or branch like a tree. There are mathematical models that explore these strange geometries, closed time-like curves where time loops back. They are highly speculative, and we have no evidence that nature works this way. But they show us what's possible within the language of relativity. They whisper of a universe where endings are also beginnings, where the farthest edge of time might be just around the bend from its origin. And perhaps, in that soft curve, space itself never ends. It only transitions into another phase of time. Let's bring this thought back to where we are. Right now, you're not just in a location, you are in a moment, held in the fabric of space-time, moving with the expansion of the universe, a participant in its unfolding. You don't float through space like a ship through water. You ride the fabric itself. The Earth moves through space-time, the galaxy moves through space-time. But more deeply, space-time moves with us. You are not separate from it. And that brings us to one more gentle thought. What if space doesn't end, because it's not something outside us? What if space and time and gravity and light are not simply surroundings, but relationships, not containers, but conversations? In this view, space is not a place, it's an interaction. It exists between things, because of things and through things. It expands not because there's something beyond it, but because the things within it, energy, matter, curvature, require expansion to be the natural rhythm of their being. And in that sense, space is not a backdrop. It's a participant, and so are we. When you breathe, you shape space. When you move, you bend time ever so slightly, and when you observe, you become part of the fabric that defines what is real. So even if we never find an edge to space, even if there is no wall, no boundary, no final horizon, we still touch the edge every day by being here, by moving, by asking. And that may be what space was always meant to do, not to hold us, but to respond to us, to stretch, to curve, to carry light from stars long gone, and to invite minds like ours to wonder where it all goes. As we continue to float through the deep questions of space, time, and endings, a quiet realization begins to rise. We do not explore the universe only through telescopes or equations. We explore it through patterns. One of the most revealing patterns is an echo, a soft residue of something ancient stretched across the sky. We touched on it earlier, the cosmic microwave background, or CMB. But now, let's slow down and listen to its whispers more carefully. This background is not just the universe's oldest light. It's a snapshot of the cosmos when it was only 380,000 years old, a mere infant in cosmic terms. Before this moment, the universe was like a foggy room filled with glowing plasma. Photons couldn't travel far without being scattered by free electrons. Light was trapped. The cosmos was bright, but not transparent. But as the universe cooled, electrons and protons joined to form neutral hydrogen atoms. Suddenly light could move freely. It burst out, filling space with a soft, uniform glow. That glow is still reaching us today. We detect it as microwave radiation, not visible to the eye but present in every direction. Even the empty parts of the night sky, those dark, starless corners, carry this gentle light. It's astonishingly uniform. The same in every direction to within a few parts in 100,000. But it's in those tiny differences, those subtle ripples in temperature, that we find deep meaning. Those ripples are primordial fluctuations, slight overdensities and underdensities in the early universe, seeds of galaxies, traces of quantum tremors stretched across the infant cosmos. By mapping these fluctuations, scientists can learn about the curvature of space, the content of the universe, and the laws that governed its early moments. The CMB is, in a sense, the furthest we can see, not just in space, but in time. It forms a horizon, a wall of light, beyond which no ordinary photon can reach us. But this boundary is not an edge. It's a limit of vision, not of space itself. Beyond it, the universe may continue. Likely did, likely does. Just unseeable. But light isn't the only thing that travels. Other signals, like neutrinos, those nearly massless, ghost-like particles, were also born in the early universe. And even earlier than the CMB, they began to move freely. There's an idea known as the cosmic neutrino background, a bath of neutrinos from the first second of the universe's life. They are incredibly difficult to detect, passing through matter like it isn't even there. But their existence is predicted, and their presence would offer a new window, a deeper look beyond even the CMB. And then there are gravitational waves, ripples in space-time itself. Unlike light or neutrinos, these waves aren't blocked by matter. They can travel through the dense fog of the early universe, carrying information from epochs we cannot otherwise reach. If we could detect a background of primordial gravitational waves, we'd be listening to the heartbeat of the very beginning. These messengers, light, neutrinos, gravity, each give us a different way to touch the past. Each one adds a layer to our understanding of space. Each one expands what we can know, even when what lies beyond remains unseen. They also highlight a gentle truth. The edge of the observable universe is not a physical wall. It's a recording limit, a point beyond which signals have not had time to arrive, not because nothing exists there, but because time has not allowed the message to reach us yet. And as time moves forward, that edge grows. The observable universe expands, not because the cosmos is expanding into something, but because more of it becomes visible with each passing moment. We are always receiving new light, always catching up to more of the story. In this way, the universe is not just expanding, it's unfolding. Like a long exposure photograph still being developed. Each layer of radiation, each quiet echo, adds another brushstroke to the picture. A deeper depth, a wider field, a more intricate curve. And we, the observers, are part of the painting, because no observation is passive. When we measure, when we detect, when we listen, we become part of the system. And perhaps that's the softest edge of all. The edge between what exists and what is experienced. Because space may continue forever, unending, silent. But until something stirs, something moves, something observes, its story remains unwritten. Each photon, each particle, each whisper of the past becomes part of that story the moment we encounter it. And so, in a way, space ends not at a wall, but at the limits of participation. Where our instruments can no longer reach, where our senses can no longer feel, where our imagination finally pauses in the hush, but the potential remains, the story waits, the light continues, and so do we. As we drift ever deeper into the quiet currents of the cosmos, we begin to realize that space, like time, like light, does not always behave as expected. It bends, it shifts, it deceives and reveals depending on how we look and from where. Tonight we arrive at one of the more delicate curiosities of the universe, places where forces balance so perfectly that motion slows and space becomes a kind of quiet harbour. These are called Lagrange points, not edges but stillnesses, not boundaries but pauses. They occur when two large celestial bodies, like the Earth and the Moon, or the Earth and the Sun, create a gravitational balance point in space. In these spots, the pull of gravity and the motion of orbit align so precisely that a smaller object can remain nearly stationary, suspended between competing forces. There are 5 Lagrange points between the Earth and the Sun, L1 to L5, each with its own flavour of balance. L1, for example, lies between Earth and the Sun. It's where we place satellites like the Solar and Heliospheric Observatory, SOHO, to keep a constant watch on our star. L2, on the far side of Earth, is a favourite for space telescopes like the James Webb Space Telescope. At this point, a telescope can stay in line with both Earth and the Sun shielded from their light, gazing deep into space in undisturbed darkness. But perhaps the most poetic are L4 and L5. These lie ahead of and behind Earth in its orbit, positions of stable equilibrium where dust, asteroids or even spacecraft can share the Earth's path around the Sun. Here, gravity doesn't pull you back or push you forward. It holds you gently, a kind of cosmic cradle. And in these places, space seems to rest. It's strange to think of rest in space. We imagine it as a place of motion, of constant orbit, of spiraling movement, and mostly it is. But at Lagrange points, that motion cancels out. The universe offers a moment of balance, and maybe that's what we've been searching for all along. Not an edge, but a balance. A place where the outward motion of expansion is gently held by the inward pull of gravity. A place where the universe says, stay here, just for a moment. But these moments aren't only local. Even on cosmic scales, balance plays its role. Galaxies, for example, hold themselves together with a fragile tension between their stars' outward motion and the invisible gravity of dark matter. Without dark matter, galaxies would fly apart. Their stars move too quickly to be held together by visible matter alone. So something unseen, dark matter, adds gravity, holding galaxies in their quiet spiral dance. This too is a form of balance, not between two objects, like in a Lagrange point, but between forces, between what pushes out and what pulls in, between motion and stillness, and this balance defines the shape of space, because wherever mass gathers, it pulls on space. It creates a well, a dip, a curvature, and in these wells structure forms, stars ignite, planets spin, life perhaps begins, all because space allowed itself to bend. It did not resist, it yielded. And in that yielding, form was born. So perhaps space does not end. Perhaps it yields into something else, not because it's defeated, but because yielding is what space does. It accepts the presence of energy, of mass, of change, and shapes itself accordingly. And maybe at the very edge of what we can know, space simply yields into silence, into smoothness, into a place where curvature flattens and motion slows, and there is nothing left to measure. That's not an edge, it's a hush, a fading away, and in the silence, a kind of sanctuary, a place where stars no longer form, where gravity no longer sculpts, where expansion has smoothed everything to such subtlety that the concept of where begins to dissolve, not because space has ended, but because meaning has. There are also speculative models that suggest the universe may recur, not in a loop but in a cycle, a universe that expands, quiets, and then rebounds. A big bang followed by a big crunch, followed by another big bang. An eternal rhythm with no final ending, just transformation. These cyclic cosmologies are not proven. They're one of many competing ideas, but they echo a soft truth, that the universe may have no ultimate stopping point, only phases, only flows, only thresholds that shift, fade, and reform. So once again we arrive where we began, looking not for a hard edge, but for a change in rhythm. Not a cliff, but a curve. Not a wall, but a sigh. Space, it seems, is not built to end. It is built to evolve, to ripple, to hold, to rest, and so are we. We are nearly at the edge of our journey, the one traced not across space, but through quiet questions. And now, with all that we've gathered, curves, horizons, whispers of light, soft expansions, we pause to ask one last thing. If space ends, where are we? Because beneath all our wandering lies a deeper longing, to place ourselves, to belong in what seems so endless, in a universe without walls, without a centre, without an edge. How do we orient ourselves? Are we drifting aimlessly, or are we precisely where we're supposed to be? Let's slow down and explore this. First, it's tempting to think of ourselves as small. One planet, around one star in one galaxy among billions. We're not at the centre of the universe, nor are we at the edge, we are simply in it. But that inness is profound, because in a universe governed by relativity, every location is central to its own observable bubble. You are always in the middle of the light that reaches you, the centre of your cosmic horizon. And so is everyone, everywhere. Not because the universe bends around you, but because that's how space-time works. There is no preferred place, no sacred coordinate. That means you're not lost in the cosmos, you are anchored in it. Not by walls, not by maps, but by perspective. Your view is yours alone, and the universe has made room for it. Let that thought rest beside you. We often look outward to measure the cosmos. We measure redshift, distances, masses, temperatures, expansion rates. But we also carry an inner cosmos, the one shaped by wonder, by awe, by the hush that falls when we look up at the stars. And if space ends, or doesn't, it changes nothing about this deeper fact. We are aware of it. Somewhere in the folds of matter and light, a pattern emerged that could ask, where does it all go? You are part of that pattern. You are part of the awareness of space. And so, in a sense, space ends where you stop asking. That doesn't mean you're the centre of the universe in a grand or inflated sense. It means you're woven into it, not a spectator, not a visitor, but a thread in its unfolding. This is not metaphysics, it's physics with a soft echo. You're made of atoms forged in stars. You're shaped by gravity, moved by time, composed of space, the iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it, born in ancient light. So when you wonder whether space ends, realize this, that wonder is itself part of space, a ripple, a curvature, a flame. And even if the universe is infinite, or finite, or curved into dimensions beyond imagining, none of that changes the truth of your presence within it. Here, now, breathing in the quiet. We often imagine edges as something out there, a place we must reach, or pass, or fall from. But maybe the edge of space is not a border. Maybe it is an awareness boundary, a place where what is known becomes unknown, where measurement becomes metaphor, where physics leans gently into poetry. And standing on that edge, you are not facing emptiness. You are facing possibility, because the unknown is not absence, it is invitation. Just as ancient light once travelled through silence to become a signal, just as galaxies emerge from tiny fluctuations in a sea of fire, your thoughts about space stretch beyond what is visible, and that too is part of the universe, not merely housed within it, but contributing to it, observing it, expanding it, not physically, but meaningfully. So let's return to the question, one last time. Does space end? Maybe it does, maybe it doesn't. Maybe it folds or fades or blooms into something else. But wherever it goes, or stops, or turns, you are in it, not apart from it, not above it, in it, not by accident. But as a result of everything the universe has done, a consequence of starlight, a child of deep time, a witness to unfolding, and whether space ends in a curtain of nothing or continues into infinity, your presence in it is enough. So here we are, near the close of our gentle inquiry. We began by asking a simple question, does space end? And found, as we drifted slowly through each layer, that the answer is both elusive and softly infinite. But before we conclude, let us look one final time, not outward, but inward, into how this question itself exists within us. Because no telescope, no satellite, no particle accelerator can ask questions. Only minds can. Only minds shaped by starlight, cooled by time, and held by gravity, can look into the night sky and wonder about its boundaries. We are not separate from the cosmos. We are not observers perched at its edge. We are expressions of it, flickers of self-awareness in a vast unfolding story. And in that story, space is not simply a thing that contains, it is a field of potential, a place for motion, a stage for time, a quiet canvas for every structure, every orbit, every breath. When we asked whether space ends, we touched threads that spanned expansion, geometry, gravity, redshift, multiverses, and the slow drift of dying starlight. We encountered dark energy, ever pushing, ever stretching. We walked along the cosmic web among clusters and voids. We listened to the cosmic microwave background, that gentle hum of first light, whispering across all of space. We bent light with gravitational lensing, watched time curve with mass, and imagined quantum ripples giving rise to worlds. And through it all, one idea returned again and again. Space does not end the way a road ends. It does not stop like a wall or vanish like a shoreline. It changes, it evolves, it fades, it quiets, it responds, and the edges we imagined. They are often limits of knowing, not of being, edges of visibility, edges of interaction, edges of time. In a very real sense, we exist within a horizon, not of distance, but but of understanding. A softly glowing shell, expanding with every question we ask. If space is truly infinite, then we are part of an endless unfolding. If space is finite, curved like a sphere, then we live inside a grand, self-connected whole. And if space blooms with multiverses, if eternal inflation births countless cosmic pockets, we remain a singular note in a deeper symphony. But in each case, we belong. Because space is not a thing apart. It is the context of our existence. It is the air of the universe, the silence between every star, the stretch in every breath. It does not need to end for us to find meaning, and it does not need to last forever for us to be real. Just being within it is miracle enough. So let us end as we began, under the velvet sky, listening to the ancient light, following starlight on its unhurried path through time. And as we settle here, just beyond the final bend in our journey, perhaps we can find peace in this. Space may never give us a final answer, but it has given us everything else. It has given us galaxies. It has given us time. It has given us each other. And it has given us the quiet gift of wonder. Let that be the ending, not a closing wall, but an opening thought. And now, as our journey through space draws to a close, we let everything soften. The questions can rest. The stars can fade. We are no longer searching, no longer stretching toward the unknown. We are simply here, settled in the hush that follows a long, quiet wonder. Let yourself remember a few of the images we've carried together. The faint red glow of galaxies drifting away. The ancient echo of the cosmic microwave background, surrounding us like a whisper from deep time. The quiet tension between gravity and expansion, always pulling, always pushing. And the thought that maybe, just maybe, space doesn't end, it simply changes. Maybe into silence, maybe into something new, or maybe it continues on forever, folding outward into gentle possibility. Wherever the edge is or isn't, we are part of what lies within, and that is enough. So breathe now, inhale gently, exhale slowly. Feel your body held not just by your bed or your blanket, but by gravity, by space itself. The same space that cradles galaxies also cradles you. The same laws that guide the stars also guide your heartbeat. In this vast ancient universe, you are not lost. You are not alone. You are a note in its quiet music, a flicker of awareness drifting peacefully beneath its velvet sky. So close your eyes if you haven't already. Let the light of distant stars fade to darkness. Let your thoughts dissolve into deep, unmeasured space. No more questions for tonight. Just stillness. Just breath. Just space. Sweet dreams.